Sorry for the technical glitch here. Um, my name is Richard Russell, and I've been giving a couple talks in the at the last couple annual conferences about space navigation. My particular interest there is that I'm a retired submarine officer and navigator, and my one of my goals here is I'm also a professor of space systems engineering at Webster University. So the uh, so teaching space navigation, things like that, is part of the what I do. But the fact that we have so many excellent observers in the amateur community, especially all the guys that are detecting pulsars, and just recently Wolfgang's Astropeeler group detecting FRBs. One of the goals here is what can we do to with the data, not just detecting it, which is really fun, but now that we got the data, what can we use that, and how can we use that for space navigation? So this is a thought experiment. So this is not fully vetted, and it's not. It's sort of like, what if what if we could do this? What if we're in a theoretical spacecraft that could get out that far? What kind of information can we get to help navigate through intergalactic and galactic space? So here, the last talk I gave was how to use pulsars, and also how to use hydrogen Doppler effects to determine your position in the Milky Way. And now, since we have fast radio bursts, we actually have information about the that's beyond the Milky Way that we can use. So the goal here is how do I use that fast radio bursts and pulsars to get spacecraft drag? And if I determine the spacecraft drag, just like you do an aircraft drag or any other space vehicle drag, for any force, newtons of force, you can determine the speed of the spacecraft. And the more drag you have, obviously it takes more force to achieve that speed. So here I was going to use the fast radio burst and pulsar data to come up with the spacecraft drag in both the intergalactic medium or interstellar medium, which is within the Milky Way, and also the intergalactic medium, which is beyond the Milky Way in intergalactic space between galaxies. Okay, so what do we get from fast radio bursts and pulsars? We get what's called a dispersion measure. The dispersion measure shows that when the energy comes in based on the frequency, it gets spread out in time. So the arrival time gets spread out. This is an indication of the density of electrons, the number of electrons per centimeter cubed that is between the originating source and the observer. That is really what is determining the density of electrons within the in that column between the source and the observer. If we can harness all the data we have on FRBs and pulsars, we can come up with the data about where all this density of matter is between us and in any place we want to travel, and from a navigation point of view. The electron density is, even though it's a number of electrons per centimeter cubed, we can convert number of electrons to basically the mass of electrons per centimeter cube, which is actually density. And that can be used in a drag formula to come up with, help us with determining of relative velocity. And as the space navigator, what I would do is I want to go as fast as possible with the least amount of energy sent. So I want to determine where all of the least dense areas are in my travel I want to go straight to my object, but it might actually be better to go, say, below the galactic plane where it's less dense, and then go in that direction in order to achieve a higher velocity with the same amount of fuel expended. So that's sort of the goal of a space navigator. I want to be plotting this based on densities. So what's the drag equation? So it's force is equal half density, relative velocity squared, area of the in the view of the direction of travel, and a coefficient of force, which is unique to the spacecraft, just the geometry of the spacecraft. So what do we know here? We don't, if we assign, what we're trying to do is trying to find out what relative velocity is. We want to find a relative velocity as we go through different dense areas of the intergalactic or the galactic medium. If I rearrange the formula, then I can say relative velocity is 2 times the force over, you see that formula. Now, if I assign, I'm going to make the assumption here that I don't care what the actual velocity is. I really sort of can't figure that out because I don't know a couple things. I don't know the area. I don't know the coefficient of force. And so I can assign density and force in there. But what I want to do is, as I go through dense areas, I want to say, am I going faster or slower velocity relative to each, the different areas. That's all I really have to know. And at that point, I can determine if I go through a dense patch, whether I'm going to go faster or slower through that dense patch. So what I do here is I'm going to assign the force to be 1 Newton. So I'm going to assume I'm going to have a 1 Newton thrust. And then I'm going to go and assign surface area and coefficient of force both at 1. At that point here is I really have a formula of the relative velocity is the square root of 2 over the density. And using that formula, I can, all I need to do is calculate density. And from what I already told you is we have an idea what that density is based on the dispersion measured from the Frb and the Pulsar observations. So what do the pulsars give me? The pulsar observations using the ATNF database, which is the Australian telescope, ATM, I forgot. Australian telescope database has all the pulsars in it, and what they do is they give you the galactic coordinates and the dispersion measure that they've calculated with that. Now what they can also do is based on the dispersion measure, they can actually make an assumption on the electron density and come up with a distance of that pulsar from the observer. Now, that's assuming a density that is constant, throughout the galaxy. That is what I'm not trying to find. I'm trying to find out what the relative densities are, and not assume that the entire galaxy is a constant density. So we're going to use the actual measured values of distance and recalculate what the electron density is from there. Australian Telescope National Facility, I had it already. And so one of the things I did do is I took the entire database from the ATNF database, and I took the galactic coordinates, and the galactic coordinates are assuming that the center of the galaxy is 0, 00 in XY, then we are about, in the Y coordinates, we're about 8.5 kiloparsecs from the galactic center. It's straight up the Y-axis. And what you'll see here is that I made this a density plot in terms of all the pulsars are plotted from their galactic coordinates from the center of the galaxy, and the little bubbles are based on how dense the density was when I plotted it. And if you look at it here, you'll see obviously the center of the galaxy is here. We are about 8.5 straight up the chart here. And you see these nice little patterns here where all the pulsars are plotted. Now, the bigger the dot is the relative density of that. But in reality, what you're seeing is that density is an artifact that it's happened to be plotted where the pulsar is, but in fact, that's the density between the observer and the pulsar itself. So that's it's a nice indication, but it's really assume a column between each one of those. What you can see though is that you can almost pick out the spiral arms here. And as a space navigator, from a first picture, what I'd want to determine is if I'm going to go fly inside the galaxy, I may need to go to least dense areas, and that might actually be between these spiral arms if I'm going between two locations. But if I actually plot that against a galaxy map with the spiral arms, you see that maps quite nicely to that, which indicates basically that pulsars are more prevalent in spiral arm regions, which makes sense because that's where the most of the stars were, and the pulsars were formed from most of the stars. So that does make sense from an astronomy point of view. That's a nice little picture there that you could plot pulsars and find your spiral arms. The formula for determining density from dispersion measure is here, and so an example here of how to convert that, and you end up with kilograms per meter cubed, and not too worried about the actual number here because I'm basically relating that to across all the pulsars. I'm applying that. This is not a constant like they have a lot of the values are. This is a variable based on the dispersion measure that we got and the distance. One of the key things that on this formula is the distance of an FRB is not necessarily known. The distance of a pulsar, some are known and some are determined through dispersion measure, which is sort of a round robin approach here. But the FRBs is going to be important to figure out what the density is. But first I have to make an assumption on what the distance is. And since the distances are in megaparsecs, and there's only very few FRBs that have an optical counterpart that has basically a distance known to it, that became very difficult. So what I did was I took the CHIME database, and the CHIME database, Canadian Hydrogen Intensity Mapping Experiment, has turned into one of the most promising FRB catalogs. They've got a full catalog of all the FRBs detected, and they've also got the information on which ones have been detected that are repeaters, and the repeaters tend to have been found to have an optical counterpart, which they're making an assumption of what the distance is. Now, these distances are which galaxy is that FRB in, because most of these, I think all the repeaters are in another galaxy. So we're talking, that's providing me my galactic distance. but there's only a few of them, and yet I've got hundreds of FRBs with dispersion measure data, and all I really need is to make an assumption of range to come back and figure out what the density of material, make an assumption on density of material between my location and the FRB through intergalactic space. This is a plot of all the FRBs from the CHIME catalog. Now, it's a lot different here because these are in megaparsecs, big distances. So if I just plotted the Milky Way, it'd be a very small piece of this right on top of it. Okay, so this is the list of repeating FRBs that we've got. And the CHIME catalog has everything about, and this goes down for quite a while. So there's a lot of FRBs done, but the FRBs, even on the repeaters, does not have any distances associated with it, but it does have dispersion measure, and it has the galactic coordinates in terms of where is my my galactic longitude and latitude direction that the FRB came from, but it doesn't have a distance to that FRB for most of the FRBs. So here, the big assumption I'm going to make on this thing, which really is, everybody will jump on me and that does FRBs, but I had to get some kind of a relative distance to the FRB catalog in order to use this against the entire 3D space. So I took these, and I took the ones that we knew the distances to, and I just basically came up with a linear approximation. I think there's five FRBs that they knew the distance, and we knew the DM to it, the dispersion measure to it. And I came up with a formula that says, based on dispersion measure, here's the distance in light years. So that plot, now what that'll do is when I take that formula and I apply it and apply that to the entire FRB catalog, I will then get a distance based on dispersion measure for all the FRBs. And from that, I can use the density formula to determine what the density is of the between the FRB and the observing. Now, since the distance is so little compared to the intergalactic space, the other assumption I made was that the dispersion measure based on just the distance in the galaxy, I did not try to just take that out of take that out. That's new. That'd be a follow-on work that to take that. You got a dispersion measure between the FRB, which is in megaparsecs away, and you got a couple kiloparsecs in between. Somehow you got to get you have to take out that the Milky Way component of the density from that. But I left that in for the moment, but that'll be follow-on work. Anyway, so from this, I came up with, applied this formula to the FRB catalog, and came up with actually the new densities for all the FRBs in the catalog, distances and densities. And here's the distances plotted. Now realize these probably are not the real distances, but from a approximation point of view for my space navigation thought experiment, this gives me a distance that I came up with mathematically that I'm going to use to actually calculate the densities using the formula. The other thing to look at is from a spherical coordinate point of view. We want to change this into spherical coordinates. I am traveling in a 3D space, and I need to, based on where the FRBs are and where the pulsars are, when I aim my spacecraft in that direction, trying to get from one point to another, I am going through these density fluctuations based on my pulsars and my FRBs, in that path. And I want to be able to, one, calculate a path to, say, my exoplanet from Earth. And then I want to be able to, based on that angles and spherical coordinates, I want to determine what pulsars and FRBs are also along that path and what their densities patterns are at the distances of those. I know that sounds right, but anyway, I put a calculator together to do that, and at this point here, I can actually my hypothetical trip to Kepler 456b, which is one of the potentially habitable exoplanets. I was able to sit there and come up with, hey, that has a certain phi and theta angles from Earth to Kepler, and what are the pulsars and the FRBs also along those angles, and what were their densities along those angles too. And big picture is, what I found was that inside the galaxy, it gives me a relative velocity, the ISM, and this number is just treat this number as a flat number, but the difference, if you apply the density in the intergalactic medium, it goes up a lot higher. So when I shift from going from the galaxy to intergalactic space, my relative velocity actually increases by about 207 times, because just the density difference between galactic space and that pulsar and intergalactic space past that pulsar. So that's really what I was after, is, can I come up with a way to, if I'm going to go to 456b, which is in the galaxy, but I want to go past that in intergalactic space, can I use that to navigate? And the answer is yes. I can. The pulsars are easy. I already know the densities there. The FRBs were different because I had to make an assumption on distance to come up with the densities. But this is an approach to do that. And obviously you can come up with a better mathematical approach to coming up with the densities in intergalactic space based on this. Quick summary of what it looks like. Inside the Milky Way to the pulsar, if you say that's relative velocity of 1, then from the pulsar to the FRB, your speed increases by about 207 times, just from density differences. Using the same force, so 1 Newton thrust, you get a 206 or 7 times increase in velocity just because of the density of drag. Okay. This just says a same. And okay, so in conclusion, we can pick out all the work that our amateurs are doing here and the professionals are doing, figuring out pulsar and FRB observations. We can use that data. It's just not data, hey, we collected the data, but now what do we do with it? So I'm trying to come up with an approach to, hey, here's stuff we can use the data, even if they're thought experiments at this point. You need to develop a tool that converts the FRB observations to density and relative velocity measurements. And then from that, you can plan trips inside the galaxy and outside the galaxy, and pick the best path to achieve the highest velocity based on density of ISM using the data from these. Follow-on work. Here I just did, one straight path, but obviously you're going to have multiple paths that you can also have. You can change the calculator to make that happen, but now you're crossing multiple lines of observations, since most of the lines are extended from the Earth to the pulsars. So you got these columns of density. But now if I do a jog from that, say I want to go from Kepler 456b to the center of the galaxy, then I'm actually crossing multiple ones. That'd be another simulation that would need to be written. I also didn't interpolate between density columns. It'd be very nice to have, if I have one thick density here and another lower density on the air, there's a transition somewhere, and that'd be nice to add in a example. And FRB distances, obviously the big assumption and thing I put in here was, how do I get an estimate for FRB distances? The way I did it just gave me a distance that I actually needed to for densities, but there's got to be better ways to come up with the FRB distances, even for the non-repeaters, which is what this estimate did. Okay, I knew that was a lot and very theoretical, so I hopefully that. If you guys got any questions?
What if you? This is Kent. What if you throw in a solar sail as your spacecraft? Are you going to have to treat it as a ship on the ocean, and you're going to have to tack the ship this way and that way to take advantage?
I think that's a great idea. It's very much like if you think of the densities almost like current, and you're trying to avoid the current that's going toward you. You want to go in the least dense area, so you get a higher speed. So I think it's very, you'd be tacking up and down. Obviously there's big, huge distances involved in these measurements, but the goal is, is there a path? At this point here, the best way to do it is actually go, if I'm going to go from Earth to anywhere in the galaxy, I'd want to go down or up above the galactic plane. Those are the least dense areas. And then I'd go across, and I probably pick up a lot of speed, which may make up the difference for me having to go vertical or to get to the least dense areas.
A fun thought process. Thank you.
Oh, this is fun stuff to do with the data, is what I was trying to do.
I have a question. The FRB is a beacon, correct?
The fast radio burst is like a single pulse pulsar,
right?
And I think there's only one in the galaxy, and Wolfgang knows all about these. But
right,
yeah,
but you're treating it as a beacon of some kind. In other words, you're getting an emission from that source in terms of an electromagnetic radiation of a pattern. So, correct?
Okay.
Okay,
right.
So now you're looking at that energy that's coming toward you from the FRB, and you're using that to calculate the density of the interstellar or intergalactic material between you and that source.
Right.
Okay. Now, the weak point is knowing the distance to that FRB.
Right.
Okay. So, for example, we use Cepheid variables to determine distances to galaxies based on the time of the change of variability. So if you had an FRB, do you think that you could do something similar if you knew how rapidly the burst changes with respect to distance?
Oh boy, I don't know. The problem with the FRBs is that you get this millisecond pulse, and there's only a couple of them that actually repeat. And they, just because you got a galactic, lat long direction that the FRB came from, you really don't know when to, it could be multiple galaxies past anything. You don't know where to stop it. The only ones that they have, I'm saying the ones I chose were the ones that they had a optical counterpart. Because there's a repeater, they were actually able to line up the other antennas or the other observatories to say, okay, it's probably that galaxy. So we're really looking at, hey, we know the distance to another galaxy. We're using that as the value. Yeah, FRBs are very hard to determine which galaxy even that's the next one, unless it repeats, because most of them you've seen once and they've never seen it again. And it's all historic data.
Well, it's an interesting concept.
Yeah, it's fun. Yeah.